Hey there, I'm Sandra Avila. I'm assistant professor in the Institute of Computing at the University of Campinas, Unicamp, in Brazil. First up, I would like to thank the organizers for inviting me to give a talk at the workshop. I feel really honored and privileged to have been invited here to share our research. Today, I'm going to talk about our quest for reliable melanoma detection in the last 7 years.
So, skin cancer, why do you care about that? Why should we, our team as Brazilian, care about that? Because in Brazil, skin cancer accounts for 33% of all diagnosed cancers. Our research lab, Reason for Complex Data, RECORD, has been working on melanoma detection since 2014. Our team is responsible for remarkable results, and we are very excited that our research has been reported on newspapers, TV news, and social media. We've been approached skin image analysis on a number of fronts: classification, segmentation, synthesis, debiasing, data augmentation. For all those fronts, we've been conducting a systematic evaluation that, not only, but also, keep us at the vanguard of skin lesion analysis. In this talk, I would like to tell you a little bit about our papers, our finds, our history. There are some crucial decisions we made that changed the game for our research. First, we decided to research on skin image analysis in 2013. So it's really cool, let's do it, but we had no data. At the time, we had no data. And at the time, there were no available public data sets. But we soon discovered that the literature was using the interactive atlas of dermoscopy, now Derm 7-point data sets. So we bought the atlas. And the fun part was that we tried to contact them by email, by phone, but we got it by fax. In 2014, we decided to move forward with deep learning. In this paper, we analyzed and criticized the state of the art on melanoma classification. We implement and scrutinize in detail one existing technique. By the way, it took us 2 years to implement it, and we couldn't reach anywhere close to the AUC report to the authors. At the time, that paper was the best we found in the literature in terms of reproducibility. So, in our paper, towards automated melanoma screening, proper computer vision, and reliable results, we discuss guidelines to improve reproducibility and experimental validity in our community. It's really not a hard task to do. For example, archive exact versions of all external programs used, provide public access to script, runs, and results. Results must be verifiable so that eventual mistakes be findable. For all of our papers, we make available code and data, and so on. We also contrast the implemented technique to two novel propositions inspired on modern computer vision at that time, of course: an advanced bag of visual words and deep neural networks with transfer learning. Not surprisingly, pipelines based upon deep neural networks outperform conventional computer vision models. Because transfer learning seems so central for successful application of deep learning in melanoma detection, our next paper studied it in more detail. Here, we attempted to answer some questions. What is the impact of transfer learning? Does retraining the transfer network for the new task help, and by how much? It is better transfer from a related medical but smaller data set from a large one related general data set or from both. The best protocol we found was to simply transfer from ImageNet with fine-tuning. Transfer learning for retinopathy, also a medical image classification task, leads to worse results than transfer from the general task of the ImageNet, even in combination. That might indicate that transfer from very specific tasks pose a special challenge for overcome the specializations, even if the source and the target task are somewhat related. In 2017, we decided to participate in the Isaac Challenge, and that was another important decision for our research, because our participation made us question the process of optimizations, the hype optimizations of the models. Our results dropped a lot, from 95% on internal validation set to 87% on test set. Our team participated in two tasks: lesion segmentation and classification. At the time, with a strategy of aggressively optimizing our models, we were ranked first in melanoma classification and third place in overall melanoma keratosis classification. We conducted a lot of experiments to validate as much hypotheses as possible. We compared the baseline VGG network to the deeper ResNet or Inception. We compared standard resolution images to double resolution images. We contrast different strategies of class and sample weighting during training. We compare normal training schedule with some form of curricular learning. We contrast different regions of training and test augmentation. We measure the impact of adding SVM as a final decision layer. We attempt to use the patient data, age and sex on classification. We attempt different model optimizes. We add different types of percent normalization, and we added a final meta decision based upon multiple models, ensemble and stack. And most of our attempts results in little to none improvement, except for the combination of deeper models and large datasets, test augmentation, per image normalization, and stack model and meta learning. But at the time, we did not have factorial analysis to quantify the contributions, and our next paper provides a systematic evaluation of the hyperparameters of deep learning for skin lesion analysis, and that I found particular game change in our research. We propose here an exhaustive evaluation of 10 factors faced when designing deep learning models. We explored the variation of those factors in two full factorial designs. Our main experiment evaluated 9 factors for 5 different test data sets, results in 2,560 treatments. Whoa! This work is unprecedented in existing art, both in the scope of the experiments and the rigor of the statistical analysis, and it's you. Our finds show that the amount of trained data has disproportionate influence, explaining 46% of the variation in performance, almost half the variability in performance. That reinforces the deep learning creed on the unreasonable power of data and has important consequences for the skin lesion analysis community. In order to move research forward, we need to create large shared data sets. So tell me something new, yeah? We know that data collection and annotation are expensive, time-consuming, and difficult to obtain. So how to create large shared data sets? Our idea to bypass this problem was to generate realistic synthetic skin lesion images. That's what motivates our paper about gen-based data augmentation. Despite the predominance of data, other factors appear relevant. The most noteworthy is the use of data augmentation on test samples. That's what motivates our paper about training and test augmentation. In our paper, Data Augmentation for Skin Lesion Analysis, we investigate the impact of 13 data augmentation scenarios for melanoma classification, training on 3 CNNs, Inception V4, ResNet, and DenseNet. Scenarios include traditional color and geometric transformer and more unusual augmentations such as elastic transform, random erasing, and a novel augmentation that makes different lesions. The best scenario, the scenario J, combines geometric, flip, random crop and rotation, and color transformation, saturation, contrast, brightness, and hue. Here, we also explore the use of data augmentation at test time and the impact of data augmentation varies dataset size. Colors in the plot, colors and marks represent the use of data augmentation. Grayscale stands for no data augmentation, orange triangle stands for training data augmentation, and blue circle stands for training and test data augmentation. The results highlight that the positive impact of using data augmentation for training and test melanoma classification models. In some cases, for Inception V4, using data augmentation can be more effective than adding new trained data. Obviously, employing data augmentation doesn't reduce the importance of adding new data, given that the network can benefit from both. This paper still remains very important to our community as a benchmark for training skin lesion models and as a guideline for applying data augmentation. Yet, in 2017, without much data but with a whole lot of ideas, we decided to generate our own data with GANs. GANs are being used to forge beautiful art and terrifying deepfakes. But for skin lesion images in 2017 and 2018, very few GANs have shown promising results for high-resolution image generation. For example, the progressive growing GANs generate celebrity face up to 1024 by 1024 pixels. And for skin lesion generations, it lacks cohesion, position malignancy marks without proper criteria. In 2018, instead of generating the image from noise, the usual way with GANs, we decided to explore image-to-image translations. So we modeled a skin lesion scenario into semantic and instance map. And this work was the first that successfully generates realistic skin lesion images. To evaluate the relevance of synthetic images, we train a skin cancer classification network with synthetic and real images, reach an improvement of 1 percentage point. And now we have realistic synthetic skin lesion images. We can distinguish real from fake, and our GANs are generating rulers. Oh, it's really amazing, and we got very excited about that. Please check out our paper. The skin lesions are really beautiful. But our Pix2Pix AG-based solution, our GAN-based solution, requires annotated data to generate images. So we start to work on different approach to generate images employing our GAN without additional data. And this story continues in our paper in the 2021 ISIC workshop. And a little heads up about that paper. Our experiments with GAN-based data augmentation show favorable results only on out-of-distribution test sets. And for GAN-based data anonymizations, where the synthetic image replace the real ones, favorable results also only appear for out-of-distribution test sets. Because of the costs and risks associated with GAN usage, those results suggest caution and adoption for medical applications. Our skin lesions were so good that we started to think about bias. Are we really augment our data sets, or it's get even more bias? So, if bias is present even in bigger and more diverse datasets like ImageNet, it's naive to think it's not present in the smaller and hard to obtain skin cancer datasets. We know, however, that there are visible artifacts introduced during the image acquisition process. For example, dark corners, mark ink, gel bubbles, color charts, ruler markers, skin hair that can inflate models' performance due to spurious correlations. Despite being impossible to wholly eliminate it, it's important to understand bias and its sources to further improve our image acquisition process and deep learning models. So, in our paper Deconstructing Bias on Skin Lesion Datasets, we propose to destroy the content information in the data and to measure how the performance of model drops. So we gradually remove content information until there is no information left to apply any aspect of medical score algorithms. Next, we use those datasets to evaluate if the network can still learn patterns with the information left to correctly classify skin lesions. And here there are four sets, and the traditional only skin bounding box and bounding box 7%. So, in the traditional, the dataset contains the usual information used for training and evaluation skin lesion analysis networks. The images contain all pixels information, and we expect to have the highest score in our test, being our upper bound baseline. At the only skin data set, to create that, we take advantage of segmentation mask. We remove the pixel information, they turn black, inside the actual lesions. And about the ABCD rule, the ABCD algorithm, we remove the C, the lesion color. Regarding the bounding box, to destroy the lesion border, we cover the silhouette of the lesion with a black bounding box. And now we have only half skin and artifacts here. For bounding box 17, to destroy size of the lesions, we define that every bounding box must at least cover 70% of the pixels. And at this point, there is no information left to apply any of the factors of the ABCD rule. Okay? So we perform single and cross data sets experiments. For a single, we train and test on the same data set, and for cross data sets, we train on Isaac and we test on them 7 points. And we found that in both cases, the networks are able to maintain a surprising amount of accuracy, even after almost all lesion information has been destroyed. Those results motivated our next work, the biased skin lesion datasets and models, not so fast. Here, we attempt to find out what are the spurious correlations explored by bias networks, and we attempt to apply techniques to debias the models, removing such spurious correlations from them. We first analyzed the possible influence of 7 artifacts present in the skin lesion images: dark corners, hair, gel borders, gel bubbles, ruler, ink marks, and patches. And we annotated by hand the Isaac 2018 and the DEM 7-point datasets. As the background may influence the results of skin lesion classifications, we propose modifying the dataset by erasing the background. We also create here what we call trap set, since bias models, by learning spurious correlations, fall into the trap and have poor performance on the test. We created a training and test set where the correlations are amplified between our artifacts and the malignance of the skin lesions. At the same time that correlations in train and test are opposite. So, by using those trap sets, we want our models not to learn about the select artifacts once they can harm its generalization ability. We employ for that a state-of-the-art method called learn not to learn for removing bias and apply to our skin lesion analysis problems. But the low performance of Learn Lot to Learn show how entangled the artifacts and the anoxylable of the lesions can be. And our conclusion here, in fact, we don't have conclusion for these papers, but it's that the state-of-the-art methods for bio-removal are not ready to cope with those sets, at least when facing our challenge trap sets. Next, our next game change, or what we think might be sort of the next game change, is the self-supervised learning. And it's open up a huge opportunity for better utilize unlabeled data while learning in a supervised learning manner. In our most recent paper, we access self-supervised for the diagnosis of skin lesion, compare with free self-supervised pipeline to a challenge-supervised baseline on 5 datasets comprising in and out of distribution samples. Our paper is the first work to showcase the importance of self-supervised pre-training for very, very, very low training dataset scenarios, less than 150 samples in our most hard test. Our plots reveal two advantages for self-supervised pipelines. First, performance tends to be higher. Second, the variability tends to be smaller. And that shows the ability of the self-supervised pre-training not only in improving the results, but also in making them more stable. For a more realistic scenario, for example, for 10% of the original training dataset and 1% of the original training datasets, the results are very impressive. Of course, models trained on small samples may suffer from severe bias, and extensive exploration is necessary to evaluate whether self-supervised might reinforce those bias again. It's hard to quantify this impression, but the models pre-trained with self-supervised learning also felt easier, faster, and more ready to use than the baseline models during the training. Nice, yeah? So, to sum up this talk, we know we have good techniques, we know we have good results, and what is missing? What is missing to make our solution available, for example, to Brazilian people? Despite being less common in dark-skinned patients, the average 5-year survival rate is 66% for Black people compared with 90% for white people. As Dr. Jenna Lester, director of the Skin of Color program at University of California, San Francisco says, if you are only trained to look at something in one color, you won't recognize it in another color, because skin conditions often manifest different on dark skin. And yet, physicians are trained mostly to diagnose them on white skin. Our skin lesion datasets barely contain dark skins. With the exception of the PAD-OS 20 from Brazil and Fitzpatrick 17, published in that workshop, none of the published available datasets include skin type or skin color labels. So, deep learning has the potential to save thousands of people from skin cancer each year, but at the same time, it's put others at great risks. Our data-driven solutions must be inclusive, must be fair. We hope our research may lead to insights to increase the chance of early detection, in particular, to create fair solutions that can generalize to reach patients in need, independent of their skin color. And that's it. Thank you for having me.